This is how this works. This is who I am. This is what I am. This is what we're going to talk about. This is the topic of the title. If anybody's not in the right spot, now's your chance. It turns out we have this thing called WebEx, and turns out we have an app, and it turns out they put these slides in all of our presentations, so we have to say if you want to use it, you can. I'll make about 2 promises for the whole thing. Number 1, I won't make stuff up. Like, if you ask me a question, I won't lie to you. If you ask me a question I can't answer, I'll just say I can't answer it. Number 2, if you put a question in there, I'll answer it. Might not be right or relevant or totally correct, but I'll definitely answer it. So the agenda, hopefully everybody sort of read this. I know everybody read this, or maybe you just randomly chose a session. I say this at the beginning of every one of my talks. If this doesn't sound interesting, there's lots and lots and lots of other interesting stuff out there. I'm never offended if people walk out 10 minutes into my presentation. Hell, I'm actually never offended if people walk out 45 minutes into my presentation, but then you've wasted 45 minutes instead of 10. All right, so hopefully what folks are here for is to hear me ramble on for an hour about how the intersection of web-scale routing technologies and service provider routing technologies either are or are not a thing depending on your politics, religion, economics, and business model. So what we're going to start with is, like, what's web-scale, right? It's a term, people use it. There's a very rough idea of what it means, again, depending on who you ask. For the purposes of the next 57 minutes, web-scale networks have these parameters, criteria, conditions, whatever you want to call them. They're extraordinarily big, like orders of magnitude bigger than other networks, which both allows them to do things that other people cannot do and requires them to do things that other people do not have to do. And understanding what some of those things are, I think, are super important in the context of building any network, but certainly building, provider networks in kind of the universe that we now all find ourselves in. At least from a compute standpoint, they are very, very heavily virtualized. This is, to some extent, the bane of the existence for all operators, right? I should have a prop that's an optical fiber. Imagine I'm holding an optical fiber in my hand. You cannot virtualize the end of a fiber because whatever is on the other end of that fiber is one thing. And with very, very few exceptions, whatever is on the other end of that fiber, when the fiber goes dark, they get pissed. And then they pick up the phone, and then they call, and then your life gets worse. If you're running a giant virtualized compute environment and a server goes kaput, maybe a web page reloads, maybe a database has to redo a transaction. These things are generally not even perceptible and almost never have really bad outcomes. In the provider world, we have some parts and an increasing share of the parts that are virtualized or can be virtualized, but not all of them. Figuring out what can and can't be virtualized is super important, right? Because the things that you can virtualize, you can treat differently, and the things that you can't, you have to figure out, are you willing to let it go dark, or do you have to have some way to protect it, whether that's in the network or in the topology or things like that. Really big web-scale networks have the ability to divide and conquer in a way that in the operator realm we often can't do, right? They're big enough that they can take layers of the network, some of which have hundreds if not thousands of devices, and say, this layer is going to handle one part of maybe a multi-level encapsulation, right? A lot of these really big web networks, especially on the transport side, are like tunnels inside of tunnels inside of tunnels inside of tunnels striped across hundreds and hundreds of links. When you're really, really big, you can do that kind of one end cap at a time, and you can optimize the systems you pick around what it's doing. In the operator space, we often can't do that. They are layered, but these two kind of go together. These big networks, they're layered in ways that are distinctly different than what we see in the operator space, and they make use of massive, massive parallelism, right? We've got customers here who say, can you do a 128 member 100 gig bundle? And I'm like, okay. And of course, as always, the answer is no. Wait. What? I can. do you have one? Like, yes. Oh, okay. Then I guess we'll figure out a way to do it. So, kind of the converse, right? Most of us live in this universe. Right? I started at Cisco in 1997 as an intern in the TAC and RTP. Spent most of my time on the routing protocols team, then what was called the ISP team, back when ISPs were like the big networks. And so I've sort of lived in this space and watched it evolve, and it's interesting because there are definitely parts that have gotten really, really different, and there's a lot of it that's really stayed the same. And I feel like we're all sort of struggling with how do we, this sounds kind of stupid, how do we adapt to the parts that have stayed the same? Because it's a little more obvious how we adapt to the things that are changing. So I'll contend that these conditions over here on the right are things that are somewhat more unique to operator networks. Right? They're not nearly as big. There are parts of them that are very, very difficult to virtualize. This combine and suffer, like I hope that everybody, well, I don't hope that everybody in here has lived it because it sucks, but I'm relatively sure everybody in here has lived through this, right? You have one place and you need to pack as much functionality as you can, whether that's into a building or whether that's into a rack or whether that's into a router or whether that's into an interface. Right, we have to combine all this stuff to try and do it in a way that's somewhat efficient. And that pushes really substantial design and implementation choices into the hardware. And we'll talk a little bit about that later. And then we don't have nearly as much parallelism, right? A lot of times we'll talk about operator networks as eyeball networks because to some extent we are in the business to connect eyeballs to content, either directly or indirectly. SP networks look much more like humans built them and much less like machines built them. The traffic fragments are much more user to machine and much less machine to machine. So we end up having to do things like follow the fiber, right? Because as it turns out, when you're trying to get content from one place to another, you end up following things like roads and railroads, and you go where the people are, as opposed to going where the water and the cheap power are if all you're trying to do is build a giant data center to let machines talk to other machines about, I don't know, whatever it is machines sit around and drink and talk about. So what sorts of web-ish things can we actually do, right? We're never going to be as big, right? Just kind of pull the ripcord, accept that, move on. Figuring out what you can virtualize and where you can virtualize it is super, super useful, right? Because they're really, really different. Everything from router selection to operating system selection to operations optimizations you can make if you do that. Figuring out how much underutilization you can tolerate to extract other benefits. And I feel like one of the hardest things that I assume most of us in here are technical rather than management, so this talk is heavily skewed that way. If you're not one of those folks, I apologize in advance, and I hope to not say anything really bad about you. Figuring out what you can underutilize and get away with, right? If I've got a long-haul optical fiber that I'm paying $1 million a month to lease, and I say, hey, I use this at 11%, the boss says, you're using 11% of $1 million an hour asset. Well, the conversation's not going to go so well, right? If I'm using 11% of something that doesn't cost me anything on a month-to-month basis and isn't terribly expensive to buy in the first place, that's a much less painful interaction to have with finance, for example. So figuring out what sort of things you can underutilize and get away with is actually a really interesting business problem. And then figuring out what kind of parallelism you can build into the network and where you should, right? So, brief segue about topologies, because one of the things that I think lots of people, and I may take this out for the future versions because it's starting to come back a little bit to sane, but I'm sure everybody went through I'm gonna do leaf spine fabrics everywhere because that's what everybody's doing and that's the cool word, and what is a leaf spine network anyway? Can somebody tell me what this thing is that I keep hearing about, right? If you wanna get, there's a really good link down here, just kind of introducing it, right? We built these, we started building these in phone switches, right? Clo fabrics were 50s or 60s, and they're using phone networks. They have lots of really useful properties. For our purposes, or at least for the Webscale purposes, really the most useful property is that they would scale almost arbitrarily large, right? You just keep adding layers and you just keep adding width. And they scale at exponential functions, right? Because every time you add a layer, you can fan the whole thing out by whatever the radix of that top level switch is. So you get into these truly, truly, truly massive, like hundreds of thousands of ports. If you engineer it in a certain way, you can also get it to where the guaranteed bandwidth between all of those ports is exactly the same. That's a really useful property for some specific kind of networks. But what it was really about was, like, they had this requirement to build utterly massive networks. And up until that point, I mean, I was one of the first TMEs to work on the CRS back when we thought we were going to build a 92 terabit router in the early to mid 2000s. That still sounds a little bit crazy, but the box was built, and of course the interconnect for almost all of these service provider routers was, and still is, nothing other than a leaf spine fabric. Right, if I take a Cisco 8800, which is the platform that I currently work on, and I block diagram all of the parts, and I don't tell you what the blocks and the lines are, it looks just like a small-ish version of the leaf and spine network. Right? If I take those, if I yank the fabric cards out of the back and replace those orthogonal copper pin connectors with fibers or copper cables or however I want to get the bits from one side to the other, it's exactly the same stuff. Right? So, you know, doing the topology for the sake of the topology is usually a really bad idea. And knowing what the properties of the topology are that make it useful is super helpful. Right? So link there, go and read that if you can't. There's a lot. Facebook actually does a really good job of being much more public about a lot of the stuff they do, because they're really an advertising company, not a networking company, where if you look at somebody like Azure or AWS or Google Cloud, like they're networking companies, so they compete like on their network, so they don't really like to talk about it. They'll go to conferences and talk about the stuff they did 5 years ago, but you're not going to see much where they talk about what they're doing right now. The Facebook folks are a little bit more open about that. So graphical version of what we just kind of talked about, right? I can take a fabric and have it inside an NPU. The Silicon One chips that I use have a crossbar in the middle. That is literally how I get bits from this port to this port, even though those two ports are something like 1.5 centimeters from each other. There's a crossbar fabric in the middle, right? It has properties that I like for building really fast network processors. I can put a fabric inside a chassis, right? The whole point here is I want to have really high bandwidth, really low cost, really low latency interconnection between all of the line cards that are in the chassis. Turns out that a leaf spine built out of exactly the same chips as something like this is a really, really useful way to build that thing. It is not a coincidence that I use exactly the same chips for selling into gigantic web-scale networks as I do for being the line cards and the fabric chips on a really high bandwidth router. Meshes. We here in service provider land have to love these because we don't have a choice, right? Most of us cannot afford to fully fabric connect in by several thousand bits, terabits, zetabits, whatever prefix bits you want to call it, so that I can build this super regular topology and eliminate all routing except send everything north until you send it south. I have to do things like follow railroads, and I have to follow the fiber, and somebody says, that building right there, I don't know, only has 8,000 watts of power in it. So I've got to figure out what fits in there, right? We've got a lot more kind of human constraints that we don't often see in the web scale. So again, they follow geography, they follow human populations, and they grow in much different ways, right? Most people in here probably have a reasonably good idea of what their growth will look like in a year, 3 years from a bandwidth standpoint, or at least we pretend we do. But you probably don't have a great idea exactly where you're going to need those links, right? You don't get to tell your customers, no, the links are going to go here, right? It's the other way around. Right. In many, many ways, the web-scale folks kind of build the network around the requirements, build the requirements around the network. And in the operator domain, we have to kind of do it the other way, right? We still have to be slaves to, you know, the demands that we get from the outside rather than from the inside, right? If somebody in the networking universe at a big web-scale company says, hey, if you change the application, it'll save us $10 million on the network. And someone in the compute world says, well, that'll cost me $5 million to do. Well, somebody above them is going to go, all right, well, if they save 10 and you spend 5, do it. Right? And then, you know, they all fight internally because that's what big organizations do. But it usually gets done anyway. Whereas I guarantee you most of the folks in here would not have a pleasant conversation with their boss if they told their customer how they were going to run their network. Right? So, with apologies to Tolstoy or, you know, whoever the whoever said it was, all web networks are fabrics and all SP networks are meshes, and this is absolutely not true. Like, one of the things that I've seen in the last 3-4 years is, like, people see something and they want to use it because it sounds cool, and then they try to take what they have and sort of force fit it to this new thing. And I would strongly suggest that folks not do that, because it usually gets you in way, way, way more trouble than it solves. So there are definitely parts of web networks that are great big fabrics, but their backbones look a lot like big provider backbones, right? At some level, they also have to follow fiber, right? Because not even those folks can just arbitrarily strike fiber across the universe in infinite quantities. All right. Little section here about systems and how they're built. Right. At least in this talk, I'll talk about 3 different types of systems, right? These are not specified. There is no RFC that says this is, by God, the only way that you can do about this. These are just the terms we use. They're relatively commonly understood. A fixed system has one thing that does all the forwarding, right? Sometimes fixed literally means you can't plug any different interfaces into it. We also call fixed things that have like little MPAs that you can slide ports in and out of, and maybe that's a fuzzy term, but we still use it. We have this idea down here called centralized. This is basically a redundant version of the fixed, where I can usually slide some type of modular I/O in the front and some type of optionally redundant, I guess I should say, optionally redundant forwarding thing in the back. Right? If you've ever looked at an ASR 1000, this is exactly the model. This is actually a diagram of the 8608, which is one of the Cisco 8000 things that we're either announcing or about to announce or have just announced, or whatever that is. And then we have the modular distributed system here, which is some set of fabric cards in the back, some set of line cards in the front, depending on how big and how tall and how much bandwidth you need. You pick the chassis that you can figure out a way to power, and off you go. Right? So, again, with apologies to Tolstoy, all single NPU systems are alike, and all distributed systems are distributed in their own way. And I make this absolutely terrible joke because there's lots and lots and lots of buzz around how we distribute or how we disaggregate systems, right? How should we? How do we want to? What doesn't work? What does work? I'm going to try to not promote strong opinions, and I'm going to have about 4 slides in different ways to ultimately assemble all of the same parts. And I give this part of the talk because I am constantly in rooms with very, very bright people who almost always have someone who doesn't have as much context saying, I need you to solve this problem, and then they use some specific buzzwords about how to solve it, but they don't really understand what those buzzwords mean. And so at some point I was asked by a group of relatively technical customers, they're like, can you help me make this stop? And I said, I don't know, I can at least try. So basically, if you look at a router, it's got an operating system, it's got a CPU that runs the operating system. If it's reasonably fast, it's got some type of networking processing unit thing that does some amount of the packet forwarding, because generally speaking, once I get to a certain performance requirement, I just can't do it on CPUs, right? It's just not, that's not true. It's inefficient to do it on CPUs, right? If you give me AWS, I can forward all the traffic you want. But at some point, it's much more efficient to do it on some type of dedicated hardware than it is on a bunch of CPUs. All right. So this is a simple router. So a big router, right? I will argue that these are all the parts, right? I have something that Cisco calls the route processor, and other people have different names for, but ultimately it's the same thing. Right? It runs the operating system, it runs the routing code, it figures out how am I going to get a packet from there to there, and it generally tells some hardware how am I going to get the packets. Sorry, how are you going to get the packets from there to there? It communicates this usually over some type of control plane interconnect. Sometimes this is PCIe, sometimes this is Ethernet, sometimes it's some other technology that's completely irrelevant to 99% of us because we don't care as long as it just works. And then if you've got a big system, you've got some set of spines that handle the traffic interconnect, handle the bandwidth interconnect, and we've got some set of leafs that do more of the work. Sometimes I have discrete CPUs that control these things, sometimes I don't, and then I've got this interconnect in the middle, right? If I look at an 8800, a big distributed Spitfire system, this interconnect is literally traces on the circuit boards that run to square connectors that are about that big and have about 400 pins in them. And I mesh those two things together, and I have now connected this link on the spine to this link on the line card, or this link on the fabric to this link on the line card. Now, right, a network of routers. This came out of a joke, I guess if you want to call it, that I told years ago to a relatively high-level executive who was bound and determined that we needed to solve a problem using disaggregation. And I said, okay, well, how do you define disaggregation? And they said something like, well, what I need is a bunch of systems that independently forward traffic, but communicate state to each other using some vendor-agnostic way to do it, and I need them to all speak relatively standard protocols so that if I want to swap this thing out with something else, it won't break the whole thing. And I said, okay, we call those routing protocols and routers, and we've been doing it since the 1980s. Right? Like, the trick is where and at what levels do you integrate things? Right? The disaggregation comment, I'm like, we've already done disag. We've been doing disag since at least the Cisco 7500, which is the first thing I can think of, where I really decoupled the forwarding part from the routing part, and where I really had a bunch of things forwarding traffic in parallel. I'm sure you can make other arguments, but I think that one's reasonable. So now, if I take a bunch of separate routers, right? Imagine I've got a bunch of 1 or 2 RU fixed boxes, and I wire them up in a way that the network operating system runs on the CPU here. Maybe this interconnect is short direct attached cables, or maybe they're AOCs, or maybe I want it to be really big and they're longer fibers, right? Ultimately, it doesn't matter. It's all the same parts, and all I've done is physically rearranged it differently, right? Now, in this case, I might have dozens, if not hundreds of instances of the operating system. That has tremendous benefits and tremendous costs, right? Managing 100 things is generally at least a little bit harder than managing one thing. But if one of them quits, that's 1% of what I'm doing instead of 100% of what I'm doing. And then I can take all of these exact same parts, right? Like this is not metaphorically, this is literally copy and pasted from the previous slide. And now I just wrap this great big gray sheet metal box around it. And I put some fans in the back, and I put some power somewhere. And now I've got all the same parts running almost the same software. And now I've just wrapped the sheet metal box around it, right? The only thing I would like for you to take away from this is not that disaggregation is good or bad or evil or any of that stuff. It's whatever you want it to be. It's ultimately, where do I want to put the pieces in a way that makes sense? And I feel like people got super, super lost in that 2 or 3 years ago. It's starting to get a little bit better. What's that? I'm sorry, I thought somebody had a question. All right, so slightly more practical takeaways. How do I scale things, right? We live in a world where scaling things is a huge part of the problems we're asked to solve on a day-to-day basis. One of my first and most important contentions is that this has always been somewhat true, and it will become more true in the next 3 to 5 years because of where the technology is going, at least on the mid to high-end space. Down at the slower speed stuff, it's a little different. But in-by fixed systems are how you scale services. And big distributed systems with line cards are how you scale bandwidth, right? Trying to force fit the opposite can absolutely be made to work, but it is not long-term sustainable. Right? And this is another thing that we'll talk about when we do the kind of the network design part is like never, ever, ever feel bad about using the wrong tool to solve the problem if it solves the problem, right? But I would suggest not to make a habit out of it, right? And one of the hardest parts about operator environments is a lot of times we're dealing with lots of managed in networks, lots of different organizationals. There's a lot of stuff going on that's not purely technical. But the technical part, we need to think about if we could do whatever we wanted, and if somebody says, hey, I need you to terminate 250,000 services in this building, The last way I want to do that is with a giant distributed router that was really designed to handle lots of bandwidth, where if somebody trips over the wrong power cord, 250,000 people don't get to watch Netflix. Right? That doesn't make, having been there, that doesn't make for a fun evening. Now at the same time, if I've got somebody who says, hey, I've got 280 400 gig E's that I want to land in one place, and I want to get all that traffic from A to B at the lowest cost and power, damn right I'm going to stack up a giant modular chassis full of line cards, because the mechanical costs of doing all that interconnect are still lower. Trust me, they're high, but they're still lower that way than they are if I drag those things across copper cables, or God forbid if I drag them across optical interfaces. So, and then the other kind of nasty side effect of this is nothing scales both, right? There is no God box, right? The marketing people, I guarantee you that there are 850 instances of the words without compromise. Wander on down to World of Solutions. Like, lie to me, Jerry, lie to me, right? Without compromise, we all make compromises, right? That's what engineering is about. It's about making trade-offs. So figuring out what the right trade-offs are to make is the super important part of what we're talking about here. All right, distributions, right? Like, raise your hand if your boss hasn't said this. Right? It's like, do more, spend less. This is why you get a paycheck. Call me when you're done. And you go, dude. All right? So, the bane of our collective existences. Hopefully, like, this is one of the other, like, 2 things that I think people should walk out of here with, right? I feel like most of us have been trying to figure out how to manage the cost of the network and how we operate the network and all that stuff with this very simple formula. Cost is the bandwidth multiplied by some number, right? And that number gets smaller over time, right? Stuff gets cheaper, links get fatter, everybody's happy. Like, anybody really, really strongly disagree with this? Feel free. I see a lot of people kind of going, that's usually how my finance people bother me. All right. What I think we should be using is that. It's got 2 terms, so maybe like 6th grade, right? The math got harder, but most of the folks that we interact with can probably manage this. And I think, like, as dumb as it sounds, we just kind of forgot about this part. And here's why I think this happened. For a long, long, long time, bandwidth was a reasonable proxy for the total cost, right? I needed X amount of bandwidth. That sort of implied Y amount of services that went with it. And systems that did really high-scale services were more expensive than systems that didn't, but not astronomically so. It wasn't, there weren't like huge multipliers in there. The distributions of bandwidth versus service, and I'm going to talk a lot about this, were not particularly wide, right? We were dragging in interfaces from end customers that were not generally were not orders of magnitude different in speed than what we were trying to match them up to, right? 15 years ago, there was no such thing as, hey, I've got an ATM over there that's got a 128K frame relay circuit, and it's going to come into a router that wants to spit an 800 gigabit Ethernet interface out the other side, right? That didn't exist, right? Maybe I had something that aggregated a bunch of 128K frame relay circuits, but it was probably uplinked with a gigi, right? The ratio was not like 8 zeros or whatever the heck it is. It's a lot. Profit. All right. Not anymore. This is one of the great and one of the awful things that the last, call it 6 to 8 years, that explosion in how giant web-scale networks have built networks has rolled into how I and my colleagues build routers and how I and my colleagues build chips. And we are now going to ship, whether anybody else wants us to or not, we are going to ship 10, 20, 40, 50, 100 terabit chips. right? I will be able to move 100 terabits across a single chip before I retire from Cisco. They might get to me and fire me first, but before I retire, that chip will be a thing, right? I don't know whether it'll be 2 years or 10 years. Actually, I do, but I can't tell you. But it's gonna be a thing, right? And yet, I guarantee you that there are gonna be a bunch of 128K frame circuit equivalents that still have to be connected to things. And that gap is so wide that the cost per bit, like that graph looks like this, right? The nice part about Moore's law in silicon and most technology is things get cheaper over time. It's the slope at which they get cheaper that you gotta watch out for. And there's this giant inflection point in cost per bit that happened in the last 6 or 8 years. And it was primarily driven by the fact that the web networks needed every single last milligram of bandwidth that anybody could give them. So that is substantially changing. Thing two, the distribution of bandwidth versus services were not particularly wide. I've got a couple of slides here in a minute that'll kind of dig into that. But again, not anymore. This is really, really changing. And then under profit, ultimately, and I do not have an MBA, nor will I ever likely to get one, but I do get to work just a tiny little bit on the business side of things. And one of the things I observed maybe 18 months ago when somebody said, you should put that on a slide. Okay, sure, I'll put it on a slide. Is that your pricing and delivery models can't be wildly out of line with your cost model, right? At some point when those things start to diverge, at some point the business becomes unsustainable, right? You can't have this thing that costs you lots and lots and lots of money and not figure out some way to charge for it. Because if you don't, eventually someone will change it and then you're in real trouble. So anyway, I promised him I'd put it on a slide, so I put it on a slide. All right. The network operator's most important ratio. If you talk to anybody at Cisco or any Cisco competitors or anybody in the network space about some of it is how do I design the network, some of it is what systems do we procure, some of it is what things do I want to think about going forward, I will argue that the single most important piece of information that you can get your brain around, and it is something that is not usually exactly quantifiable, is the ratio of how many bits do I need to move versus what do I need to do to those bits, right? One of them is the bandwidth, and the other is the service, right? I'm still trying to figure out exactly what terms I like. I have to use terms that people know. Maybe service plane, maybe data plane. To me, service plane kind of has some baggage that isn't terribly applicable here. But ultimately, the data plane moves the bits, right? And then the service plane figures out what do I have to do in order to move the bits, right? There's a really big gap between there's a label on this packet, look it up, send it right. And this thing's coming in, it's got a tunnel label, a backup label, a VPN label, an entropy label. Then I gotta dig through all of that, figure out that it's an IPv6 packet, figure out what in there I wanna hash on. I've got 17 different output tunnels that I can unequally weight the output. I gotta do that lookup. And I gotta figure out what the label stack is to put back on the packet on the way out. Oh, and by the way, I had to check an ACL twice on the way in. And then I gotta dig through half the packet to figure out what kind of QoS policy I wanna put on it, and I gotta store all that crap somewhere, and yada, 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 you see where I'm going, right? So the ratio of how many bits am I moving versus how much work am I doing to move the bits is super, super, super important, right? It is ultimately my job to figure out how to build something that will do all of this stuff, and I will continue to do yours to figure out how much all of this stuff is ultimately worth, because it costs me a lot more to do that than it does to just move the bits. Fancy charts. Okay. If you were to say, on the horizontal axis, these are my service speeds, right? These are my 128K frame relay circuits going out to every ATM with a little teeny tiny frame relay, come on. It's probably Metro Wireless or something now. But it doesn't matter, right? They're super important circuits because it turns out banks don't like having their ATMs turned off. Also ask me how I know that. But you gotta keep these things up, but you gotta count things, right? You can't just arbitrarily say, here's an IP address, it'll probably work, right? Some of this stuff, they actually want it to work, and then they actually want you to prove that it's working, and then they actually want you to be able to defend it when it doesn't work. So I have to keep all of this state, right? But I've got this somewhat broad mix of, right, I've got this case where I've got a bunch of really low speed interfaces that are uplinked to a couple of high speed ports-ish, right? This is a relatively standard aggregation type router. Importantly, this does not say port speed. This says service speed, right? That's a super important distinction, right? I might be dragging 84,000 pseudowires in on 100 gig E, but it's still 84,000 services, right? I've got to keep 84,000 somethings in a table somewhere so that I can discriminate between number 101 and number 102, right? So again, super important. It's not port speed, it's service speed. Over here, I've got another, I actually pulled these from a couple of customer routers. Here, this is also super common, right? I've got every different service speed under the sun. I've got everything from a few 100K to tens of megs. Maybe I've got a whole bunch of giggy connected customers, right? I've got all these kind of lumps in it. And then over here at the right side, I've got my super high speed uplinks, whatever they are, right? So I call these provider-like distributions, right? Most operator networks look more or less like one of these. You can certainly argue. What they almost never look like is that, right? You build a giant web fabric, all the ports are the same speed, right? There's an extraordinarily large, very, very well-known fabric Webscale customer who an incredibly large fraction of their network is built from equipment where every single port on every single device is exactly the same speed. And it is just wide and tall. And there's lots of other knock-on effects for why they do that and how they do it, and there are some things that it lets them do, and there are some things that it makes them do. But that distribution would literally be a single bar, right? And then you've got something like over here where, like, you've got a whole bunch of, this used to be giggies and 10 giggies, and then it was 10 giggies and 40 giggies, and then it was 10 giggies and 100 giggies, and now it's 100 giggies and 400 giggies, and you see where I'm going, right? But again, there's a very, very small number of services because they're basically just main interfaces with maybe a really basic QoS policy and the ports. And that's all it does, right? And those are really, I build really different systems to address those two different things. So, takeaways. The distributions really matter. They matter much more than the average bandwidth, right? Almost nothing is less relevant to how we do our jobs here than how much total bandwidth or how much average bandwidth is in the network. It doesn't matter, right? Makes no sense. Do any of these look like yours? And do you have a good idea what it's going to look like in a year or 3 years or 5 years? Like, if you want to think big picture about your network and how you're going to scale it and what are you going to do, this is a hard question. This is a really hard question. But I'll contend it's a really important question. Because there's a bunch of stuff in here that doesn't make a lot of sense if you don't have some context to that question. All right, so some of the things that I will argue. On the operator side, I did used to run a relatively big university network. It's been a while, but I have run a network, and I certainly spent enough time in TAC that I spent a lot of time driving broken networks. So the total bandwidth will continue to grow, but I think it's going to start getting a lot slower. I think we're starting to see this. I think we're starting to hear people actually say it out loud, which was kind of a taboo thing for a long time, right? If you were an operator and said, no, my bandwidth really isn't going to grow all that much, everybody would lose their mind. And I think some of that stigma is going away. I will contend it's going to be more and more unevenly distributed. To me, the big open question here is, what is IoT actually going to become? Because if IoT is a bunch of tightly managed, really low-speed sensor circuits, then that pushes a whole bunch of low-speed scale out onto that far left edge of the network, or that far left edge of the distribution, right? That sort of stuff. Obviously, at the high side, people are going to continue to want really high-speed pipes to connect other things. But again, I think the gap between fast, this is all relative, between fast and slow is going to continue to get wider. One of the things I've really gotten into recently, and a coworker of mine kind of turned me on to this, is there's something called a zip distribution. This is a person's name who came up with it whenever they came up with it. It basically says that there are tons and tons and tons and tons of things in human existence that follow power laws, right? The easiest one of these is the 80-20 rule, right? You get 80% of your bandwidth from 20% of your customers, or you get 80% of your revenue from 20%, or whatever it is, right? But the curves are all shaped like this. And you can stretch the axes just a little, but they're all power law, right? They're all log charts if you want to plot them on something that's readable. And that stretch between fast and slow, to me, is super important. And as it gets wider, it gets even more painful to manage it with kind of like a single thing, which kind of leads me into the next section of the presentation here. On the vendor side, right, this is my part of the world. I'm relatively confident about most of this stuff, but I don't live in this universe every single day, but I do live in this universe every single day, and this stuff is for sure gonna happen. The MSDC universe is going to drive astonishing bandwidth and density improvements, right? Like, I'm gonna walk in here at some point with a chip that's that big and go, that's 100 terabits. The silicon's going to continue to get leaner, because the only way for me to move that many bits is to start figuring out how to do less work per packet, right? Some of it, it's not gonna fall off the end of the universe. We're not gonna get to, although there may very well be places where we basically do turn it back into just a label switch. But the amount of stuff that I'm doing at the high end in the silicon is gonna get really, really fast, and it's gonna get leaner. We're gonna see more and more and more utilization of fixed systems rather than modular systems, right? This is a huge topic of conversation in my part of the world. Some people don't like it. Some people seem to think it's going to get, I'm 100% on this. Because what I'm, in the operator universe, what I'm not going to run out of is bandwidth, right? When I can put 20 terabits on a single chip, I'm not out of bandwidth. I'm out of something else, right? I'm going to run out of faceplate ports because I mean, if I'm trying to aggregate gig-E's, turns out 20 terabits is, I don't know, 10 racks worth of physical ports, right? I'm not going to be running out of bandwidth. I'm going to be running out of something else. I'm going to be running out of ACLs or sub-interfaces or policers or counters or, I don't know, but it's not going to be bits. The ratio of the cost for big high-speed long-reach optics is, like, that ratio is going to continue to get wider. Right? It's already really, really expensive to buy the optics for these things, right? Everybody who's tried to buy a relatively fast system recently goes, whoa, relatively speaking, that box is cheap, but man, those optics are really expensive. That's just gonna continue. This is just a physics problem, right? As I try to look at a light wave that comes in on a fiber and the electronics go, a 0 or a 1? Right, the number of transistors that I need to do that 800 billion times a second, like that curve is also not linear, and the cost to do it is just going to keep going up. And then the other thing is, like, my silicon team is going to hand me chips faster than I can actually get them into systems, which means I'm probably going to hand you systems faster than you can consume and onboard them. And this is going to be like, and I get it. Like, I'm never going to give you what you want fast enough because that's the role of the vendor. And so, but like the number of like different things that you're going to see on roadmaps and all that stuff is going to be even wider than it has been in the past. So let's talk for about 15 minutes about my super generic how I would build a provider network if I could from scratch, which of course is completely irrelevant because nobody ever builds these things from scratch. I think this is a relatively fair description of most operator networks, right? The stuff in the middle is meshy because it's got to follow the fiber. It's expensive because those links are either you have to pay somebody else every month to use them, which the finance people hate, or you own them and you don't have very many of them, which makes them expensive internally, or you have them, you have a lot of them, and you can sell them to someone else for a lot of money, which makes the finance people want you to use less of them, right? But it's the transport thing, right? And it's expensive. And again, if you go to your boss and say, hey, our transport is running at 85% utilization, they're probably not going to give you too much of a hard time. But if you go and say, hey, our transport is running at 15% utilization, it's not going to be a fun conversation. All right, so let's zoom in a little bit, right? You can call this a metro, you can call this a pop, you can call this a region. I don't care what we call it. It's kind of this sort of really generic diagram, right? Again, these light blue links, this is the expensive stuff, right? These are these really, really expensive optics that connect to really, really expensive links that either you own or you buy from somebody or whatever. These systems do not have to be terribly expensive, right? This is, like, if these are the spines or the aggregators or like whatever noun you want to wrap around them, like, these boxes can be super cheap, right? And the stuff in the middle can be relatively inexpensive. These can be either super short reach fibers or direct attach cables, right? That sort of stuff. And then the complexity all ends up down here, right? Because these are where the people who pay your salaries live, right? We need to keep them happy, because if they don't pay our salaries, then we don't get to come to Cisco Live next year and listen to some idiot talk for an hour. And these links, we often don't have a lot of control over, right? So figuring out, this is kind of the hook for the whole presentation, right? This is the adapting Webscale technologies and topologies to the provider, or whatever the heck I called it. I think we're gonna end up building something that looks mostly like this. Now, there will absolutely be places where it can look like this and all of this stuff can be in one box because it still fits, right? I was the first TME on the ASR 9000, and in our world, because I had to stack up line cards to even get to a usable bandwidth number, I built a bunch of different modular systems, right? And I had fabrics in the back and they had a lot of silicon, and I plugged cards in the front, and that was how I got the bandwidth and I got some scale to go with it. With these newer systems, I don't need to stack up cards to solve a bandwidth problem. And stacking up cards to solve a scale problem doesn't really work. It never really did, but now it's like the relative ratio is even more different. So I think we're gonna end up building stuff that looks more like this and less like really big 1 or 2Z boxes. Who does this, right? Who has things that are called core? Like you look at the Visio and you go, oh, this is the core level. And they're like, what's that? Like, oh, that's the insert gigabit customer, right? It used to be gigabit, then it became 10, then it became 40, then it became 100. They're like, what's that doing on the core box? They're like, oh, well, Marcus over in sales said that, if we could land this 100 gig in 2 weeks, we could sign a $74 trillion contract with What's It Financial, and that was where we had a port, right? Everybody's nodding, and it sucks when you do that, right? And the real problem is not that it sucks. The real problem is that it breaks this model, and it's okay right up until you want to change this, right? Like when you want to change this, and all of a sudden, now you're like, what am I going to do with that port? Because the thing that now can drive my transport costs down by like an order of magnitude, well, I can't terminate 100 gig with 20 sub-interfaces and a bunch of things because the new version of the box doesn't do all those features yet, right? So figuring out a way to sort of isolate, maybe a strong word, maybe not, kind of isolate the interfaces and land them in a place that makes sense is like a really important thing. All right, so this is kind of, same sort of thing, right? I feel like we're gonna end up building networks like this, right? These things are gonna be spine switches, like core router. Core router sort of implies long haul, and I don't know whether that's a thing or not. I can put 400 gig long reach ZR plus type optics into these otherwise really, really inexpensive 1 and 2 RU systems. They don't use a lot of power. They're mechanically really friendly. If I need to replace one person can walk in with the switch under their arm and slide it into the rack, right? I've replaced backplanes on 16-slot GSRs. Not fun, right? Swapping out a 32-port 1 RU switch, way more user-friendly. And so if you'll grant me that these boxes are relatively cheap, it's the links that are expensive, right? It's the optics and the links that are expensive. But I don't have to have, if I leave these things half full, it doesn't matter, right? I don't work in sales and I don't totally understand our licensing stuff, but I've been led to believe that you don't have to buy the whole box, right? And if you don't have to buy the whole box, and really if you don't have to put all the optics in it, then it's really not that expensive. right? Having empty ports sitting there doesn't really hurt, right? The interconnects are not terribly expensive, right? These systems, the uplinks are not terribly expensive. And so now the trick is, what do I do with A, B, and C, right? How many of these different things do I need? Like, I probably need something that is optimized for landing interfaces, customer services, whatever you want to call it, where the ratio of the bandwidth to the service is very high, right? 10 gig, 100 gig direct attached customers, hey, I want a BGP session, the full table, and 100 gigs. There you go, right? Totally different than, hey, here's 80,000 double tagged VLANs that you need to put into a pseudowire head end and parse all of this stuff with counters and meters and blah, 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 right? The system design, and I could do 4 hours on how the chips are different, and I would love to. If anybody wants to talk about that, see me later. Like, the difference between those two things is already pretty wide, and it's going to get wider, right? So figuring out, and then you get into, like, to some extent, you get into an optimization problem here, right? If I've got 10,000 customers, I just need 10,000 different routers, all perfectly optimized for that customer. We all know that's not a real thing, right? But the other side of that, like the other side of that thought experiment is that somehow there's one router that can efficiently enough land all of those customers in one place. And I just don't think that's true, right? And I mean, there's probably nobody on the planet that loves the ASR 9K more than I do. That thing made my career. But I can't do it, right? Like when people start throwing like lots of 10 and 100 gig at me, it's too much power, it's too much money, it's too much space, like, to do all this stuff efficiently. But at the same time, I've got somebody who's handing me 100 gig and going, hey, there's 84,000 double tag pseudowires on here. I'm like, I don't have anything else I can land that on, right? That system is perfectly optimized for that sort of use case, right? So figuring out how many of these, and you know, I'm contractually not allowed to tell you that, hey, if you build it this way, it's totally vendor agnostic, right? You can put whatever you want here. Like, I have some strong thoughts. I'd be happy to talk to you about some of the wonderful products we sell down at the world of blah, 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 blah. But there's nothing that stops you from putting whatever you want down there. And so, like, I feel like from a design standpoint, like, you sort of have to eat this part up front, but it's really not that much money. It's not that much money, it's not that much space, it's not that much power, right? And as long as this is scoped day zero, you can just grow this stuff and you can grow it as you need it, right? You don't have to know in January what this layer is gonna look like in December, right? Because you start with a bunch of empty slots. You can almost think of this as a big modular chassis where you get to choose later what line cards you want to put into it, right? If you sell a whole bunch of services where they're really high-speed interfaces, you put these boxes over here that are optimized for doing that. If you sell a whole bunch of interfaces that are really low speed and really high touch, you have some other box over here, right? And you go these things from the right and those things from the left, and maybe you have another thing in the middle. That becomes a joke and call it an Excel optimization exercise, right? Which is how much money is onboarding one more thing worth. And again, the ratios, it can be whatever you need it to be, because you don't have to know in advance, right? So I've done a 2-hour version of basically that previous slide, the summary of which is the transport is really expensive, right? You need to optimize there. The red links, like, these were never really that expensive to begin with. They are cheaper now, and they're going to get cheaper, right? What it's going to cost for me to move 100 gig between two routers with not a lot of services going on, that number's just going to keep going down, right? So, like, optimizing is always good, but this isn't where you're going to save tons and tons of money, right? And then figuring out what things here make sense for this network, right? That's where the really interesting questions lie. So again, this is not a prescription for a specific number of levels. It's like you might very well need to hang some other thing down here if somebody says, I got 285 physical gig E's, and I got to land them somewhere. You can stack up more at A, or you can do some type of aggregation thing, right? I don't want people to walk away going, oh, it's got to be 2 levels. No, it does not have to be 2 levels. It probably often doesn't need to be more, but there are certainly cases where it will. It's not a prescription for specific types of systems, right? There are absolutely networks where these things you may need enough bandwidth that these things can be big modular systems. For most people, I don't think it will be, because like I have 25 terabit routers that can be these levels, right? If 256 by 100 isn't big enough for a spine, that's a pretty big network, right? And then, again, I don't have a prescription for a specific vendor. I do have a preference, but I don't have a prescription, right? You can make that box whatever you want. We talked about this a little bit. This is the slide for when we talked about this, right? Over here, you have your web-like distributions, right? Lots of really high-speed interfaces. Over here, you have much more telco-like, right? This is your canonical, I don't even remember, 28 DS0s in a T1, something, right? Whatever it is, you multiplex and channelize and all that stuff, and each one of them is a circuit, and they've all got 27,000 different counters. But figuring out like what that ratio looks like and what the service speed mix is super important. All right. And then the business impacts of this, right? Align the service offerings to where your growth is, right? If you think you're gonna sell a whole bunch of low-speed services, then you're gonna have to find a way to land those services and land them at a cost that somebody's willing to bear. And one of the things that I think is gonna be tough for everybody is, I think, your customer base, and by extension, my second order customer base, still wants to pay by bandwidth. And I think we're gonna have to figure out how to get around that. Because at some point, they're not paying for bandwidth. They're paying for bandwidth, and they're paying for whatever the services that we're doing. The ratios, the control plane to data plane ratios are super important. And then, I don't know the answer to this question. Like, does the stuff that's currently in the middle exist in 5 years? Like, is what are now gigabit and down, like between gigabit and 100 gigabit, do we have end customers that do that in 10 years, 5 years? I don't know. I can definitely make arguments either way. So please fill out your surveys. So every year, I normally put in a slide that says something like, somebody spends a lot of money for you people to come here. Somebody spends a lot of time and effort putting all this show together. You've just wasted 58 minutes and 15 seconds of your life listening to me blabber on. I hope it's useful. Like, I really enjoy doing this. I've been at Cisco 25 years, except for the year I went to a startup and tried to build networking chips. If you put something in the WebEx, I will answer it. If you come and find me, I will answer it. If you tweet at me or email me or ask me a question, I will answer it. I think it's super important that you get something out of this. Hopefully the last 58 minutes and 45 seconds were not totally wasted on everybody. If you fill out your surveys, we do read the comments. I know you're not supposed to on the internet, but we read the comments. And evidently this year, if you fill out surveys, you get socks. So there's this. Everybody knows about this. Thank you. You can scan the QR code. And I will be either right here, unless there's somebody immediately after me, in which case I will be right out there, and we can talk about whatever you want. Thank you.